So have you ever seen a 1.58 dimensional shape?
No, I'm sure I haven't.
I'm sure you have, and that's what I would like to talk about today. Do you remember the video we did 8 years ago about the chaos game? I just rolled 2, so I need to go halfway to the point that has been chosen at random. What we did in that video was we had 3 dots. We started with another dot somewhere, and we chose a dot on the corner at random and moved this starting dot halfway towards that dot. So we could have gone up there, and then we could have gone down here. And we did that hundreds of times, I think, and got bored. But then I did it on a computer, and the structure emerged. So come and have a look at this. So what I've got on the screen here is the same 3 dots on the same starting point, which I can move around. But you can see I've got 3 other dots. And these are, if I went to each of the destinations, all of them. I didn't choose one at random, I just did all 3. 2 things are going to happen. We're going to get a lot more dots a lot more quickly. We've got exponential growth of dots, so much so that my computer will break if I let it go too many levels. Exponential growth does that. But also, otherwise, it's exactly the same process and the randomness is gone. The same structure should emerge and it's much quicker and cleaner. So here's the reminder. Let's crank it up. Here are the 3 dots. I realise they're kind of tiny on the film, but we don't need them to be much bigger because when we do another level of it, you can see each of those dots has turned into 3 more dots. And I'm losing the original dot each time. I'm just turning it into 3 and 3 and 3, and I'm just going to keep doing that. And either this is familiar, or you've just been amazed all over again or something. So this is the Sierpinski triangle. Some people call it the Sierpinski gasket. I think that's an odd name. Apparently Mandelbrot called it that because it looked like a piece from an engine with holes drilled in it. And it's shapes like this I want to talk about. The starting point is that the chaos game is a really good way to generate these shapes. And so come and have a look again, because once we've generated it like this cleanly, the nice thing about having a toy like this is we can move things around. So I can move these points and the shape moves with it, and it doesn't have to be an equilateral triangle and all that stuff. And we can do a couple of other things. We could generalize, we could have more than 3 points. And the other thing we could change is that instead of jumping halfway towards the point, we could jump a different proportion towards the point. We could jump 1/3 of the way or 2/3 of the way. I'm going to do a couple of others. I'm going to change the number of points to, let's have 4 of them. And you can see that I've made a different pattern. And if I crank up the number of iterations, you can see the pattern is different. And again, we can move this around and something intriguing is happening. This is an easy way of generating fractals that look pretty and give us a chance to talk about them. Let's do 5.1, and I'm going to change the length that you jump each time. You can see that changes how the pattern works. Now we could do this all day. I don't want this video just to be about the pretty patterns, but you can see there's a particularly nice one there. I can increase the detail. Got a fractal with a sort of fiveness about it. Now these are all fractals. I've used that word repeatedly, and a lot of people will have heard that word. I suspect you've heard it too. I've used it about other things like the Mandelbrot set. These are all fractals that we can describe, and I want to tell you a little bit of the backstory about why we call them fractals and why the dimension of these things is maybe not what we expected. So that's my plan. Here is a square, famously 2-dimensional shape. The idea is a 2-dimensional thing. Here's the big idea though. I want to scale it up. I want to make it bigger. If I make it 2 times bigger, I think it would look like this. And I'm going to say 2 times the size. It needed 4 copies. Do you agree with those numbers?
Yeah.
1, 2, 3, 4. Notice something else. 2 squared is 4. I know you know that. That 2 is that one, and that 4 is that one. And this little circle here is important. For example, if I made it 3 times bigger, let's do it over here. How many copies do we need?
9.
I agree. So 3 times the size, 9 copies. 3 squared is 9. That 2 is the same 2s up there. This is a massive clue about what you knew already. This shape is 2-dimensional. And actually that's the 2 that's telling us it's 2-dimensional. And just as a quick sanity check, let's do it in 3 dimensions. Imagine a cube, 1 copy. If I want to make this twice as big, how many cubes there?
8.
I agree. So twice the size in terms of length, yeah, and we needed 8 copies. Do you know what I'm going to write next?
2 to the 3.
2 cubed is 8. So this 3 here is telling us that this is a 3-dimensional object. I hope this is not a surprise, but it's nice to see that the numbers we're using for dimensions are actually sort of a mathematical feature of how things scale up. And we're so intuitively used to that we kind of forget that's what's going on. Incidentally, if we did this with a line, you'd need 2 to the power 1 or 3 to the power 1 to get it 3 times bigger. You just need 3 copies of it because that's 1-dimensional. Now, that means this reasoning is available to us for any shape. We've done it for 2-dimensional shapes and 3-dimensional shapes. Let's try another sort of shape. Here is a shape, Brady. You may have seen it recently, but we're going to do the same argument on this one, which is faintly surprising. I'm going to make it twice as big, but if I make that image twice as big, it would look like this. And I reckon that's twice the size. Are you happy with that? How many copies did you need?
Well, it looks like 3.
1, 2, 3. Because of the hole in the middle, I only needed 3. Unlike the 2-dimensional shape where to get it twice the size, I needed 4 copies. So because this is a strange shape, and by the way, I'm assuming this is a mathematically perfect fractal and it's holes all the way down and all the stuff has happened. And that's why I can copy it, but I don't need to copy in the middle because there's a hole. So the calculation is exactly the same. Let's do it on paper here. 2 times the size, 3 copies. So just like this one, I needed 2 times the size, 4 copies. I need 2 to the power something giving me 4, and this time I need 2 to the power something giving me 3. And that is less obvious to me.
Where's your something?
Well, I'll put an X in. And we can solve it with logarithms. Do you want to know the answer, or shall I solve it?
What do you want to do?
So we'll do it quickly. Okay, I can do x log 2 equals log 3. X is log 3 over log 2. It doesn't matter what base of the log it is. This comes out to be approximately 1.58 ... I'm not going to do the rest of it. It's an irrational number. Brady, you have seen a 1.58 dimensional shape.
Yeah.
That's annoying, isn't it? I can see your face.
Well, using one definition of dimension.
Correct. That's exactly what we're doing. I'm using the definition of dimension that relies on how things scale. There are others. This one might be called the Hausdorff dimension by some people. There are others to look up. The Minkowski dimension is out there as well. There's a bunch of others. Mathematicians are trying to capture what we mean by the word dimension, which is interesting because a lot of people use that word without being aware of a technical definition, and that's fine. This is one definitely technical definition. How things scale is how we think about it, because it's very intuitive for 2-dimensional shapes and 3-dimensional shapes. But this shape is not intuitive, and it has a different sort of dimension in the way it scales. We're going to try it on some other fractals, if that's all right.
Is 1.58 unique to the Sierpinski triangle, or is
No.
there's a whole family that have that many dimensions?
And we'll see that in a moment, in fact. But what it's doing is capturing a property of that fractal, and other fractals with the same dimension would have similar properties, even if they looked a bit different. Do you want to see one? I mean, we're off on a... Come and have a look. What I can do is, very quickly, is show you that our original chaos game, if the proportion is a half, looked like the Sierpinski. But all of these, however I move these points around, would scale in the same way. Now, I'm the first to admit they look really similar, but they are not the same fractal. In fact, you could have a right-angled one or somehow squash it. But because there are 3 points and the jump was a halfway, it's going to make a shape that has this scaling property of a 1.58 dimensional shape. So there are others, and these are some. You can see they're subtly different, but there might be others with a different structure. They would have some similarities. Let's look at a different fractal. So I think this is often called a Sierpinski carpet. It looks like if you're thinking of a 3-dimensional fractal, there was a Menger sponge, which I remember 10 years ago, trying to build a big version of with Matt and Katie all around the world. This is one face of that thing, if you remember that. It's a fractal. You can see its structure. It's got holes in all the way. We're going to try and figure out how it scales and try and come up with a dimension for it. Spoiler, it will be different to the other one. So if I shrink that down, the easy way to make this shape repeat is to make it 3 times bigger. Because of the way it's structured, that's the next one that's easy to repeat. Are you happy that's 3 times the size of the little corner bit?
Yeah.
In length. So how many copies did it need?
Oh, I've got 3, 6, 8.
I agree. Not 9, because of the hole in the middle. So 3 times the size, there are the 8 copies. We need to solve the equation this time. 3 to the power something is 8. Long story short, 1.89. Again, it's an irrational number. It's actually log 8 over log 3. Doesn't matter about the logs. The point is, it's not a whole number, but this is the way this shape scales. And it has a similar vibe to the Sierpinski triangle, but it's a squarey version. And here's what I like. And so however annoyed you are about this way of naming the dimension, it is actually quite an intuitive thing. That Sierpinski shape is full of holes. In fact, it's literally full of holes. It's holes all the way down. That's kind of the weird property of it. And yet it's taken up a space. So here's the thing. It's not really like an area, which would be a 2-dimensional shape. But it's also not really like a line, which would be a 1-dimensional shape. And so in a very hand-wavy way, I'm kind of pleased that we can give it a number between 1 and 2 to capture the fact that it's not like a line, but it's also not quite like an area. So recognize we're doing something weird, but we're having to do it because it's a weird shape. But almost by definition, it's not a shape. It's all holes. And this one's also full of holes, but here's where I'm glad about this numbering system. It's still holes all the way down, but it feels less holy than the triangle one. It feels more like an area to me, even if it's not, which is why I'm glad it comes out with a dimension which is high, it's closer to 2 than 1. So that's what this Hausdorff dimension is, an attempt to capture something strange, but it does capture it in what I feel like is an intuitive way, which I like.
Are all numbers available to be a dimension?
I don't know off the top of my head, but I can certainly show you some numbers that maybe you weren't expecting. All numbers is a big topic. Like, are we talking real numbers? Are we talking rational numbers? These are irrational. Are all of them available? Because there's a lot of them. And that's at least 3 other videos, Brady.
Also, another popular game is imagining what it would be like to live in a 4-dimensional world or a 5-dimensional world or a 2-dimensional world. And we have books and films about it and stuff.
Flatland is a classic.
Flatland, of course.
Wonderful story. This story is fitting in that thought experiment place of Flatland.
What would it be like to live in a 1.58-dimensional world?
Confusing. Is my only answer. Let's hold that thought experiment for another time, because there are still some consequences that we can answer more easily to see. I want to bring the idea of fractal dimension back to our chaos game, because it turns out the way the chaos game works is a really helpful way to see that. So with our triangle, we saw here, this is a 1.58 dimensional thing. It had 3 points and the jump was a half. That was important. If we're going to do the carpet, we need 8 points because of those 8 copies. Let me show you how that looks. So I'm going to drag this up to have 8 points, but then I need to put them in the right places. They're all over the shop at the moment. So I'm just going to spread them around. These are the 8 positions where you kind of get a scale copy of the original. This is how the chaos game works. It's actually just enlarging or shrinking the original picture, whatever it is, to be a copy in a certain scale in a certain position.
And when you place a dot, how far does the dot jump to a...
In this case, it's not halfway. If I had it at halfway, you see you get this fractal, which is, I'm not even sure what it is. It's different. But if I go 2/3 of the way towards the points, then it does start producing the carpet, and here we go. So what I'm trying to point out is that the way the chaos game built a fractal is using exactly the same numbers that we've been playing with to get our dimension. Is to do with the number of copies, and that's the number of points in this game. That means we can play with any chaos game and get a new fractal with a different dimension. But there are some surprising ones. So here's one that often people try. Let's go back to our original, the Sierpinski gasket. There it is, 3 points. The natural thing is to do 4 points. And let's say, well, let's put them in a square. That feels like a natural generalization. So let me show you what that does. They're in a square. I'm still jumping halfway towards each point. And if I crank up the iterations, we get disappointment. Now, even on the Wikipedia page, I checked yesterday, the page on the chaos game says if you try it with 4 points in a square and jump halfway, you don't get a fractal. And I don't think that's true. It's just not obviously a fractal until you play with it. So I want to show you the moment that this video, I wanted to make this video, and it happened here. I built this in GeoGebra, I was disappointed, I was like, well, that's boring. The rest of the fractals are nice. But because it's in a tool which I can interact with, and this is why I always seem to work on these sort of tools, as you may have noticed, you can play with it. So I grabbed one of the points, but I'm going to move this point around. And this is the point that made me realize, oh, wait. So it is a fractal, or at least it has that property to it. And you can kind of see the 4 copies happening. It's much more obvious when if they're actually in the square, it's an illusion that they're not there. There they are. But when I started dragging this around, I was like, this feels 3-dimensional.
Yeah, like it's going over the top of it. Yeah,
right,
yeah.
it feels like
you're holding the top of a pyramid or something.
And then I thought, well, a tetrahedron pyramid is a 4-point structure. So what I need to do is see this in 3 dimensions. And then I realized, well, why have I been doing the chaos game in 2 dimensions all this time? Obviously, I'm chatting about dimensions. I should free my mind from those 2 dimensions and go 3-dimensional. So let's have a look at what happens if you do the chaos game with 4 points in 3 dimensions. Here is a 3-dimensional plot. It's on a black background. The points are very tiny, but I need them to be tiny so when I crank them up, they don't swamp everything. These points move around, by the way, and you see the points move with it. Let me crank up the iterations and show you what you get. Some of you, I'm sure, will have guessed. Here is the 3-dimensional structure we're getting. But there's something to be wondered at, because there was a moment when we did it in 2 dimensions that it didn't look like this structure at all. It kind of vanished. And you can kind of see that happening if I get it right. I'm going to slightly leave that alone. We are seeing a tetrahedron. In fact, if I put it to a regular tetrahedron, there it is. This is maybe called the Sierpinski tetrahedron, and it's a lovely thing. It's a tetrahedron pyramid, so it's not just any old pyramid, it's like the purest one. So I think this is a nice realization, but there's something mysterious about this one, and you can see it occasionally when I get the angle just right. You're like, well, what's going on when I get around there? We should calculate the fractal dimension of this shape, and you know how to do it.
But I'll let you do it.
Well, and here's one. A friend and colleague of mine printed this really nicely. Here it is, a 3D printed fractal tetrahedron. What's the fractal dimension? Well, we need to think about how many copies we need to make it bigger. You can see the copies. So you can imagine one of the corner copies being the small one. When you scale it up to make the one I'm holding, it's twice the size of one of the smaller copies. Do you agree with that?
Yeah.
So we're going 2 times the size, and I think we need 4 copies. 1, 2, 3, 4 copies. Do you agree with that?
Yeah.
So 2 to the power what equals 4?
2.
Correct. At this point, I haven't mentioned the word fractal I've been using. It was actually coined by Benoit Mandelbrot. It was a portmanteau of the words fractional and dimension, or dimensional fractal. It's become so ubiquitous that people forget that's what it means. So all these shapes we've been doing, Benoit and Mandelbrot characterized them as having a fractional dimension, which is why they're weird. However, this one, also weird, pretty, really like holding it in my hand, has a dimension of 2, which is not a fraction by most people's heads. It is a fraction for mathematicians, right? It's a rational number, 2/1, but it's an integer. And this does not feel like it has an integer dimension, neither does it feel like it is an area, which is what a dimension of 2 should feel like. And yet, if you look at it just right, a 3-dimensional shape, which I'm going to argue this feels like it is, I'm holding it, you only ever see 2 dimensions because you're seeing a projection of it. Now, if I get this just right, I'm going to close one eye and line it up with the camera lens. You're seeing essentially projections of this shape, but if I get the projection just right, can you see that?
Square.
And you've already seen that on our Chaos game. This shape must have some flavour of area about it because it has dimension 2. Despite it existing in 3 dimensions, there is a projection which is exactly an area. So I can drag this shape around, but if I just pick the right direction, the shape's gone, and there's the square. This particular fractal dimension is an attempt by mathematicians to characterize the properties of these beautiful shapes. There's a reason why a lot of people are obsessed with fractals. I include myself. They are like peering into infinity, and there's some sort of thing you can't really get to grips with. But this is an attempt to get to grips with it. And what I'm really pleased about is that my intuition isn't abandoned. The fractals with all holes in that don't look like lines have a dimension between 1 and 2. A less holy version feels like it's higher dimension. If you look at something like this ends up having a dimension between 2 and 3. This is a Menger sponge. It's not quite 3-dimensional, but it's definitely not an area, so it ends up between 2 and 3. And then sometimes you get a fractal with dimension going back to being an integer again. This is dimension 2. And although it doesn't feel like it, if you just look at it in the right direction, boom, it is an area. The calculation is an attempt to wrestle with something difficult, but it does capture the weirdness in ways that I was really pleased about. And so this is a story of me playing with something I knew. I knew this had dimension 2. I also knew that there was a projection of it that looked square. I also knew the Chaos game looked boring when I did a square. And then the penny dropped when I dragged the pointer. I was like, oh, of course, I'm not seeing a square. I'm seeing that tetrahedron just from the perfect angle. But as a final comment, this does not have dimension 2 in just one direction. But then there's also this direction.
Yeah.
And there's also this direction. There are actually 3 directions which it gives you a square. Maybe that's not a surprise. What's also nice about tetrahedron is that it fits inside a cube perfectly. Hideki Suiki printed these little shapes. Here's the tetrahedron inside a little plastic cube. He calls this an imaginary cube because if you look at it from the side, you get a square. If you look at it from the other side, you get a square. And if you look at it from that side, you get a square. In fact, every direction you look at this from, it's a square. It has exactly the same properties as a cube would. It looks square from every angle. So this is an imaginary cube, and it's not the only one. What he did really nicely was found a couple of other, what he calls imaginary cubes, and he printed them. He made them fit inside a cube. They're more complicated shapes that I'm not going to talk about in detail in this video. What I suggest is checking out the work of Hideki Suiki to see his explanation of these things. But just to show you them, here is something he calls the T fractal. And if you look along that aspect ratio, square again, and that one, square again, and that one, square again. This also has fractal dimension 2. And here's another one he calls the H fractal, which is built off a hexagonal bipyramid. There's a square, a square, and a square. And actually this has 6 different directions of looking like a square. This is still what mathematicians are exploring. They're playing with geometry of shapes which fascinate them and coming up with new ways of exploring. And actually, Hideki's published some papers on which directions can you look at this from and see a shape which is not just all holes. And then it gets kind of technical, and if you want to go look that up, really lovely thing to do. I really enjoy playing with fractals. I also really enjoy that the Hausdorff dimension, which we've been looking at an approximation of, does capture something which I still find intuitive. It's kind of a relief as a mathematician.
Well, you made it this far, so if you'd like to see a little bit of extra footage from this video, I've posted some over on Numberphile too. I'll also put links on the screen, in the description, in the comments to more videos from Ben Sparks. And a very special thank you to all our Patreon supporters, including those whose name you see on the screen at the moment. Supporting us on Patreon helps us make more, bigger, better videos, and I also try to occasionally arrange little treats, extra footage, prizes, perks, things like that for our Patreon supporters. Check it out, links in all the usual places.
Ratio, and keep the fractal dimensions in, and you don't rotate those copies, then this would still be an imaginary cube, even if there's smaller copies in there. And you do that ad infinitum, and this is what you get. So this is the fractal built of this triangular antiprismoid. Hideki called it the T fractal, because T for triangle.